now I understand. And this n is like a parameter. This n is a parameter.
Yes.
Okay, very good. So now let me make a comment. Now my comment.
Okay.
This scheme is what many people call it the nudging, and they tried all this. As you said, there's a long history, but this scheme is not the right one, and this will not converge. And let me tell you why, or let me mention, if I have a minute, how did we come to the nudging scheme to begin with? It was based on turbulence theory, because classical turbulence theory asserts that there are finite degrees of freedom in turbulent flows. And Poyash and Prodi in 1967 showed that if I know the low Fourier modes of the solution in 2D at least, then the solution will follow. And as a result, probably what has to be nudged is not Vn toward V, but some reference solution to the G of V. Namely, you have to match the filter with the filter, because here you have a leftover and it will never converge to the solution. And that's where basically our contribution was in comparison to what everybody was doing nudging, because there was no mathematical theory to support that. So there's a theorem which will tell you what it should be done. So this nudging is not the right nudging, unfortunately.
So what do you say? So, sorry, say it again. You say that you want to solve the equation only for on the support of the field.
No. What I'm saying something simple. Look, I'm saying something simple. You write your equation as is, but in the nudging should be coarse scale nudged toward coarse scale. Period. And what happens to the fine scales? They will follow.
This is what we do. This is what we do.
No, but you have V. But you have V, not.
Okay.
Wait 1 second. Let me explain. This is what we do. I mean, I told you here there is an extra filter, G, that apply the nudging only on the position where we have the data.
Okay, good. I think we can move to the last question, which is Prasad Perlikar. You want to turn on?
Yeah, I have a question. So the question is that the data on which you are doing the machine learning or the nudging is strongly rotating turbulence data, right? Where you have a strong rotation. And so the field is very two-dimensional. The question I had was that if you didn't have rotation and you had just hired in on, or even for your rotation data, if you looked at components which were perpendicular to the direction of rotations. So in the sense that, VZ statistics. So instead of VX, if you look at VZ statistics, does that thing also reproduce equally well? Or if you were doing homogeneous isotropic turbulence, does that work equally well as, the strongly rotating case that you have?
No, okay, there are two questions. So the first question is that if I apply to the vertical plane the same kind of inpainting, it works well. I mean, I have to train, of course, also on the vertical image.
Yeah.
It works well. For the three-dimensional case, it's a bit more complicated, because if you want to be strongly turbulent and 3 dimensions, you need to supply a lot of data.
Okay.
Otherwise, you are too sparse. And I mean, we didn't try, but I am a bit pessimistic that you can really reconstruct a 3-dimensional configuration with this kind of machine if the flow is strongly turbulent. If the flow is smooth, there are already other examples that people have already done.
Okay.
Thank you, Luca.
Thanks so much.
Thank you to you.
So we learned last night that there was the passing away of Professor Narasimha. So we will have a minute of silence in his commemoration. And then there will be very short talks by Srini and Rama Govindrajan.
So notice what I'm asking is very similar to what this person asked. This first comment here, Umberto Guriato, says, is the neural network used for the generator a convolutional neural network? So this person is saying if the neural network, basically the network that uses some sort of neural mechanism to make the algorithm work in the network by understanding the neurology of everyone's mind, is that network used for a generator? And is this generator used as something bigger combined with the neurological network that is being used for the algorithm? And I think it's interesting how somebody has already asked this and I didn't notice. And the way that I'm asking similar is in these two comments. Infinity minimizers depend on the structures and turbulence of the polyism coming from any transmitters when connecting to our neurotransmitters. Because remember, our neurotransmitters is just a connection to other transmitters that are not organic. We are the, you could say, the only organic neurotransmitters. So I believe that yes, our neurotransmitters are being used for other neurological transmitters that are not organic but are synthetic. In order for them to work, they need to feed off of the neurotransmitters that are organic in humans. So I'm asking, if that's the case, is there a way to neutralize it from our transmitters first, causing a turbulence on the polyism itself? Notice how I generalize polyism and I also generalize infinity minimizers, and I and generalize the transmitters in itself, because there's transmitters in space that are actually satellites. These are also transmitters, towers, 5G towers also. So that's why I generalize it, because there's many transmitters that are interfering with our natural turbulence, and it's misdirected with the polyism and the infinity minimizers that control the frequencies that keep us all in this matrix. So that's why I'm here, but nobody has answered my questions yet. I have to restart. But I watch this channel often.
Us to define our own problems rather than guiding us too hard. So he would give us spectacular ideas in our work while seeming to allow us to be doing our own thing. And in any discussion, he was hugely democratic, like the youngest student could be right. He had that concept. And of course, his profound understanding of fluid mechanics was something. This was just one picture which is written in his own hand that I wanted to share with you. This was work that Aaron did as a single author when he was 24 years old. So here is a boundary layer, and which is laminar at this end going through instabilities as the Reynolds number increases. And it's breaking down into turbulent spots which are growing and going into fully developed turbulence. So up to this time in 1957, people would believe that these spots could be born anywhere in the transition zone. Whereas he came up with this very simple model of a concentrated breakdown. And that immediately change the whole picture, and and everything in experiment agreed with this model, and it was a kind of paradigm shift in the way people thought about this problem. And he was 24, and it was a single author paper, so he had deep mathematics, experiment, and results of this kind. That's about all I wanted to add to what Srini said. Thank you for your attention.
Thank you.
Asimo, I think Uriel wanted to say something.
Okay. Please, Uriel.
Become muted. Yeah. So yesterday I shared the very bad news from